Today I want to talk to you about this. This was my diploma thesis. It's about photogrammetry. Photogrammetry is a computationally complex topic, so the maths behind it is simply complex. And in implementing this, I kind of stumbled upon a thing called functional programming. We already heard about functional programming today. We heard about like the views and the transforms and function composition as a tool for low-level optimizations. We also heard about some other stuff. And I kind of want to go from the other direction. I want to talk to you about high-level functional programming as a tool for high-level application specification and kind of relay my experiences about that. Oh yeah, photogrammetry. Photogrammetry means that we measure things inside photographs. Usually what we do is we have multiple photographs of something, of an object, and we want to calculate the shape of the object in the photographs, the three-dimensional shape. So it's kind of like the inverse of computer graphics, of rendering, where you have like a scene and want to render it. Here you have some photographs and want to calculate the scene. For example, down here you see a bunch of photographs, this little triangle, and they could be photographing this kind of building. This is like a top-down view, and in the end, if you just have the photographs, you want to end up with these little camera positions and some 3D representation. And there are a bunch of softwares for this. For example, Photosynth and Agisoft and Autodesk Recap and Capture in Reality and so on. These softwares, they are really good. They're really solid. They can do these photogrammetry tasks. They are usually used for things like this up here. This is a screenshot from a game, and games and movies usually use these kinds of procedures for creating assets. But the real problem with this kind of software is basically this. This is a simple Hello World example from a popular open source photogrammetry library. And what you see is a bunch of, allocate these data structures and mutate the lists and so on, and it's super, super complicated. I mean, of course, you could really go there, you could really understand this kind of code, and that's well and nice. But if you try to do something new, if you want to experiment, if you want to do structural changes in the algorithm, if you want to have something completely new, try to rearrange parts and so on, this gets exponentially difficult. So it's basically impossible for kind of researcher, for kind of people working alone, trying to change this, trying to understand this, trying to implement new ideas and new things into existing photogrammetry softwares. And of course, the commercial products are usually closed source, so there's no chance of really doing something there. So what we want to do is we want to implement it ourselves, basically. Now, how can we do that? If we want to do photogrammetry, we start with some kind of camera model. The camera model is the mathematical representation of your camera taking the pictures. You have like this pinhole camera up here. We heard it already today. A simple camera producing an image of an object, which is characterized by a set of parameters. Important, if you want to do photogrammetry, then the standard maths is usually formulated in terms of pinhole cameras. So if you have real photographs like this, they have a whole bunch of image artifacts, for example, the lens distortion and so on. So you want to usually revert the real camera to a pinhole camera, for example, through lens undistortion, which takes these curved shapes and makes them straight. There's programs that do this for you for some camera manufacturers, or there are also some OpenCV functions that can numerically do this for you. Then we take our pictures, and when we take our pictures, we need to identify the things that we want to reconstruct within a picture. this is really, really important. If you want to do photogrammetry, then please choose those image features which represent your objects adequately. So, for example, basically all softwares use key points as image features, which are basically points of interest in the image. That works out for many tasks, but not for all. For example, this wall over here, this white wall, key points wouldn't be a good idea here because the wall is basically white. There are no features. Whereas, for example, here, like lines or something like this, maybe polygons, there could be different approaches which could be used to reconstruct something here. And it's important to be able to experiment in this kind of level, to be able to take your features, invent new ones, exchange some, and so on. Okay. Then you've taken your photographs. You have your features. And then you need to do a step called feature matching. Feature matching means that we identify the same feature across multiple photographs. So we have multiple photographs and track the same object, and we usually want to do that automatically. This is, again, something that's really, really critical. The feature matching has to be good. You need to have few mismatches between shots, between images, but you want to have a really stable set of matching features. Your feature matcher needs to respect the baseline. The baseline is the distance I have taken between shots. And if I take a large baseline, I have really nice depth information in the two pictures. So the disparity has like lots of depth disparity. But the features, they look less and less alike. So the perspective distortion will make the features different. And this is like kind of the very, very basic conflict in feature matching you need to solve. There are many different approaches to feature matching. Let's look at a little function signature here. We can now, just from this, define a very nice little function signature. This is our feature matcher. And it's basically a function that takes one set of features. I use a list here. A second set of features from the other images and produces a set of feature pairs. So there's no complicated things here, just a very simple function signature which every feature matcher must in some way fulfill. We implemented kind of our own feature matching in this. We have this idea that features that are close together must move in a consistent fashion. So we have like these patches of moving features. And it's not too complicated an idea. Basically, we take the features, we have their positions, but we also have their motions, their movements. And then we basically just put a bunch of Gaussians on them, this one here. And then we transpose the problem and make a least squares solution for all the input matches we have. And then we get like a neat little prediction function which tells us, okay, these features move as a group or these features move completely wildly. And works really well. Let's look at the implementation. So we can implement this simply after we have calculated this prediction function, simply as the filter operation. So we have like some kind of sets. We use immutable data structure here, and then we just filter them and make sure that the set of resulting feature matches has a super nice properties, the properties we want. So we introduce some kinds of parameters here, and what we do is we take the function, partially apply the parameters. So we fill out these arguments with specific parameters, and then we remain with the free parameters with the function signature that we defined previously. So everything just fits really neatly into our nice function signature. From when we have like a set of matching features, we have two images and matching features in between, and then we can calculate three-dimensional partial geometry from it. This is kind of also a bit of an involved progress, but there's algorithms for this. For example, 8-point algorithm and 5-point algorithm for the point features. And what they do is they just take sets of features and give you a least squares three-dimensional scene structure. Then when we don't have two photographs, so we have many photographs, and the process for making many of these reconstructions iteratively is called structure for motion. So what we do is we start with some camera at some point. We have to identify the base camera, for example, and then we put another camera, and with the post-recovery, put another camera, and so on, and we get iteratively a larger and larger and larger set of reconstructions. Yeah, and the code for that could look like this. So if we say we have our little set of images in the beginning, it's a set, and this structure for motion thing is just nothing more than a neat little set reduction. So we have the set and add one of these pictures, add another one. So the set gets smaller and smaller and smaller, and then in the end we get one single like geometrical thing. And the actual reduction function is basically this here. So for every new camera that we encounter, we can just add the new camera to an existing one by putting in the geometrical pose that we calculated using the feature matches we got from here. So it's a really neat little system where these functions just provide the argument for the next function for the next function. So it really composes well. And in the end, because it's an iterative process, you usually want to do bundle adjustment. So you take one finished geometrical construct, one photo network, and then there's these measurement errors from the iterative algorithm, and you want to rectify them with one global optimization step. This thing just makes small adjustments, and there are solutions for this. And we just say it's a cute little mapping function here. Yeah, and so a final photogrammetry pipeline looks like this. We have some photos, then we extract some features, then we do the post-recovery, then we bundle adjust, and then we do something else with it. And this looks really nice, doesn't it? This looks really amazing, because the code got super small, super clean, super concise. We have a really nice little linear reading order. We have the program is specified to the algorithm designer's intent. Look at how nicely we put a little optimization here. We could simply write, instead of an array map, an array parallel map. This worked because we used immutable data structures, and immutable data structures can be trivially parallelized. Each of these functions are, again, just further composed functions, as we defined them previously. And all in all, it's just a very nice, very clean syntax, and we can easily just extract some parts of this program, and they're, again, standalone programs, which we could reorder and optimize and implement differently. So it's really nice. It works out this way. This function composition thing gives us a very good, very nice little program, and this is basically what I would really call a hello world example. Because someone can sit here, someone with no domain knowledge whatsoever, could understand this kind of code, could go inside and then specialize. So this is basically kind of almost a domain-specific language for photogrammetry. Simply created not through interfaces, not through memory allocation and so on, but through simple language features like functions compositions, higher order functions, and so on. And yeah, this here reads like pseudocode, but this is an actual implementation. We used this reference implementation to create some results in the scope of this diploma thesis. Here are some reconstructions, and here I think this was like 60 cameras, this was like 20 cameras, and 300, and so on. And this is like a really promising thing. As a future work, we will use this to create specialized photogrammetry pipelines for buildings and for reflective surfaces and so on. This using functional programming has really cut down on our prototyping time, made this iteration thing really fast. Gives you a lot of confidence because the computations, you can prove them that they are correct, and so on. If you want to see the code, it will be it will be online later this year under this link, but you can just come to me, talk to me, and I'll be very glad to talk about this topic, but it's really exciting. Okay, thanks. The question was, what's the runtime? The runtime for this simple reference implementation is obviously slow because it's just a reference implementation, but with tricks like this parallelization, and you can also trivially do memorization where results are cached and so on. With this, subsequent runs get faster, and you can really cut down on your like experimentation and prototyping time. But for really a final production-ready code, you would obviously do some really low-level optimizations in the end.
Okay, let's thank
Attila, thanks
again and continue on.